Module 7, you need to allow some extra time for this one this week. So this is the point at which a lot of students are just tired of ice charts. And I hear you. I hear that everyone gets tired of ice charts. This is the end of the ice charts right here. Starting next week after the test, it'll be all different material. So that's the good side. The negative side is that you still have to deal with ice charts, and it's kind of the most complicated one. So I feel like the material kind of peaks in complexity this week. And it's not even because you're learning something new. It's just because you're taking something you already know, and you already twisted it once to figure out for the salts. But then now you're going to twist it a little bit more to do buffers. And then for titrations, you are going to have to pick which ice chart method works. So that's the other thing with that one. So anyways, with buffers are regular old ice charts. Here we go. Except that we actually have a value here. And normally you don't have it. Normally those are 0 and 0, but we have a value. And when we have a value, there's going to be a trick with the x where you can get rid of that x and you can get rid of that x. So it means that when we fill this in over here, we're going to have x times 0.2 times 0.1. So you can solve it with an ice chart. Or, even better, we have this little handy-dandy equation that if you have the initials for what you would put in an ice chart, and you can just fill in the equation, and then you're good to go. So that's kind of a shortcut for doing buffers. Now, the final part of buffers has to do with actually making a buffer using a reaction. So you're also going to learn about ICF charts. F meaning final. This is not an equilibrium. So I didn't mean to write that with a equilibrium sign. That's a straight on arrow. And in this case, you have an initial amount for several things, and you subtract whichever one is smallest from the left side and you add it to the right. So that's what's going on with this 0.05. Subtract it on the left, add it to the right. So we get some final values. Once you have those, then you can go back to the Henderson-Hasselbalch and plug it in. So that's buffers. That's what you're going to be learning about buffers. So it's very, again, method-based, not as much use equations-based. All right, now for titrations, you actually did a titration if you were on ground for Gen Chem 1. If you haven't, then that's okay. A burette is something that has like this little knob on it, and it just lets you drip base into a container. You can make titration graphs as you drip stuff in. You can see that it'll start like in one section and then it'll eventually curve all the way down, or it could start in a different section and it'll eventually curve all the way up. So those are titration graphs or titration curves. And you can learn about them. They have like 4 main looks, and so you'll learn about those and identifying what kind of a titration it is. But generally speaking, for a titration, there are 4 stages to it. The first stage is a weak acid. And if you remember, you learned how to solve for a weak acid right up here. So you'll work it just like you're solving for a weak acid. The second stage is a buffer. So you learned that one earlier in the week. So you'll solve it like that with the Henderson-Hasselbalch. And then the third stage is a salt. And you learned about that stage over here in the soluble salts. So you learned about how to do that. That's that one that had the little funny flippy-roo with the K values. And then you're going to end with strong base calculations. That was actually something you did at the very end before the last test. Wait, where is it? Right here. Oh yeah, strong base calculations, where you ended up figuring out like the moles of NaOH and how you can, if you can turn it into just moles of OH, you can plug it into that POH expression and get the POH and then convert it into pH. So, I mean, the thing about the titrations is, again, it's not new. The methods aren't new. You just need to make sure that you're applying them at the right times. And then finally, we're closing on insoluble salts. You learned about soluble salts. Well, we're closing on insoluble. Here's the nice thing about insoluble salts is that they start off as solids, and so there's nothing on this side. So what it does is it makes the math really, really easy. You just plug in x here and x here, and it's x squared. So it's just, if you have x, then you just square it, or if you have case P, you take the square root. So that math is really, really, really easy. You also will do common ion. And so common ion is where basically we fill one of these spots in at the top with a number. And it actually also makes it easier because let's say that this is like 0.1. By the time I get here, it's 0.1 plus x, but then I assume that the x doesn't matter. And when I plug it in, I get 0.1 times this x, and see how easy that math is? And then that just equals a k number. So you don't even have like a square root involved when you have common ions. And then finally, we're going to do Q versus K. Now, I said this earlier, but way up here, you learned about Q versus K in Module 4. See it? Q versus K and shifting. So it's that same principle. So if you can look up K and you have some K values over here that you just look up from a chart, and if you can calculate Q, then depending on which one is greater and which one's lesser, if the K is greater, when I turn it into an arrow, it means that it'll be no solid. If the Q is greater, then when I turn it into the arrow, it'll mean solid. And that's the big question that they ask on these is, will there be a precipitate? Basically, will there be a solid? Now, the way that these are worked is a little bit different. You already, like we already talked about, like this is the K for AgCl2. So this is the K already. We already talked about it. We switch it over to Q because we have a reaction we're doing. Now, this makes him, this is that. AgCl makes that when it's dissolved in water. This one doesn't matter because it always dissolves all the way in water. So what we do to get the Q is we have to find the match for Ag, and it's right there. I've color-coded it, so it's 0.1. So what I'll do is I'll plug in the 0.1, and then over here I've got to find the match for Cl, and that's what it is, and that's 0.2. So when I solve that, that gives me my Q. And again, like I said, I get the K from a chart, I compare them, and that's how I know if they're solid or not.